Everybody know who Michael Jordan is? Famous basketball player. He's missed more than 9,000 shots in his career. Lost almost 300 games, 26 times. I don't know if he really kept track, but 26 times he was trusted to take the game-winning shot and missed. He's failed over and over and over. And that is why he is successful. The only way you will be successful is to do physics over and over and again. Practice making mistakes and then learning from those mistakes. That's the only way. There are no shortcuts. This is true for almost everything you do in life. It's true in sports, it's true in music, it's true in physics, it's true in all of education. Thus far, we have focused on treating complicated objects as points, point particles, and we have not worried about their internal rotation. The only time we really worried about that was when we discussed how these pool balls worked, how billiard balls work. Then we did. Now we're going to discuss how to do that in a more rigorous way. Turns out that almost everything we've done so far has a corollary, an analogy in rotation. All right, so we're going to be concerned with rotation. Here's the goal. We're going to start by looking at just rotation of a rigid object. All right, so I'm going around in a circle. I'm pretty much a rigid object. Not totally. I have some fluid in me moving around. But to a good approximation, I am a rigid object. What does that mean? What it means is the particles inside my body do not move much relative to each other. They move together as I rotate around, right? They move together. But they don't move relative to each other. So that's what we mean by a rigid object. An example of a not so rigid object, I guess I don't have anything else, but I'll use this, is this. That's a not so rigid object. All right? The keys can move around relative to each other. Made up of rigid objects, but each of the little objects themselves, the whole system is not one rigid object. The motion of each of the individual pieces of this, very complicated, and we won't do it. Right? Probably you can't do anything because there's too many details you have to know. So we've already done a little bit of work because we've already looked at a particle moving around in a circle. So we know how that works. Right? We know the variables that we use. We have for translation, we have the position, the velocity, and the acceleration. For rotation, we have the angle, theta. We have the angular velocity, omega. And we have the angular acceleration, alpha. All right, so we already have kind of the ingredients that we need to discuss rotation. So when I talk about my rotation, I could talk about where I am now as theta equals 0. And then when I go around, my theta increases, right? And when I come back to where I was, I've gone around 2 pi radians, but 2 pi radians is the same as 0. So we have that. We can also look at how fast I'm moving. I'm moving relatively slowly now and actually slowing down, or I can move faster. The faster I move, the more dizzy I get. Is that a physics thing? Maybe, maybe not. Also, my rotation can change its angular speed, in which case I have an angular acceleration. All right, so right now, I accelerated initially, but then probably slowed down. So this angular acceleration is analogous to angular velocity. OK. We also know there are some relationships between these variables. If this is a circle, and we're looking at a particle moving on the circle of radius r, we know that if I draw an axis, I could call this length S, and then I know S equals r theta, V equals r omega, A equals r alpha. That just follows from pure geometry. We've already seen all of those. So now we need to describe rotation. The fundamental starting point for linear behavior, for translation, is the concept of mass. Mass determines how much an object will accelerate given a certain force. So the larger the mass, same force, what happens to the acceleration, up or down? Larger mass, same force, does the acceleration go up or down? Down. What's the analogous quantity for rotation? We're going to have something that's going to cause me to turn. We'll learn later. We call that torque. And then we also have something analogous to mass. And that's called moment of inertia. So this is the moment inertia. And its definition is this. And we're going to motivate this definition. What is Ri? What is Mi? I have an object. It's rotating like that. This is the distance Ri. And there's a mass, little mass here, Mi. And this is the whole object. Ri is the distance from the piece of the object to the axis of rotation. So this thing is called axis of rotation. So one of the odd things about the moment of inertia, it is a property of an object. It depends on which axis you choose. The moment of inertia about an axis going through my head down through my toes is different than a moment of inertia about an axis going this way. And you have to work it out in different cases. Let's start by looking at the kinetic energy of a purely rotating object. Now what I'm going to do is I'm going to derive that kinetic energy in a little table, and there's going to be little pieces in that table missing. And your job is to fill in those pieces. So we're going to look at the rotation of a rigid body around an axis. So rotation of a rigid body about an axis. All right, so I'm going to make a little table. We're going to compute the kinetic energy. So let's make this table. First step is I'm going to say VI equals RI omega. And the reason for that, so VI equals speed of ith particle equals distance to axis. And notice omega, same for all particles. Now I want you to fill in what's the kinetic energy of the ith particle and what you did to do that. And then the kinetic energy for the whole thing. And I'm going to start by just writing this. But then you have to fill in the rest and give a reason. And then finally, we get K equals 1/2 I omega squared. So here's what you have to do. 3 minutes or 5 minutes, 2 or 3 minutes. I'm going to call on somebody and ask them what they put in here or what they put in here, here, here. OK? So everybody write something down. Go to it. Fill that table in. What do you think goes in there? We should be ready. Ki equals 1/2 mi vi squared. So that's good. Can you go any further? What does this equal? Good. Was that hard? Not that hard, right? What do you think I should write here? Anything? What can I write there? We used, here we could give this number. So we're using 1. So that's good. That's true. We use that. We should write that down. Is there anything else we should write down? I mean, how did we even get from here to here? This may not be obvious, but we have to say that the kinetic energy of a particle is 1/2 mv squared, right? That's what we mean. But it's a definition that the kinetic energy is equal to 1/2 mv squared. That's a definition. So we're using a definition for kinetic energy. And one way we can write that is with 3 lines. Everybody know that? If we write 3 lines there, that means it's a definition. What about the next step? What would you write in the next step? So I already did this part. Now I want to do the next step. What would you write? All right? Now, I want you to consider doing something, adding something to that result. Can you see what I would like to add to it? It's not quite, there's a symbol. I want to put a couple symbols I want to put on here to emphasize something. Anyone think of what I want to do? Thinking ahead? What's this sum a sum over? What are we summing over? I. All right, so we should put that in. And do you notice anything about each of these 3 terms? Omega is the same. So I want to put a little parentheses around that to indicate I don't need to put omega inside the sum. And so this uses the fact that omega equals the same, all I. And all I'm doing is summing over all particles. All right? All right, so now I have that. And that's the answer. What should I write here? I equals this sum, mi ri squared. And that's a definition. So using this definition, using this, I can replace this by I. Right? OK. We're going to do an object rolling and rotating. I want you to take your coin, and I want you to make sure you notice what is at the bottom right there. OK? And then I want you to turn this coin without it slipping. I want you to measure how far this dot moves along here. So after a while, it'll be like that dot will be over there. It's rotating this way. And then over there. And then it's going to come back to here. So this position on the coin will be back to there. And I want you to measure this distance. So do that very carefully. Don't let it slip. That's going to be hard to do. All right. Who has a number? Nobody? What? Did you do it? What did you get? 8.1. 8.1 what? Centimeters? All right. And what kind of coin is that? $1? $10? All right. All right, 8.1 centimeters. All right, anyone else? 7.8, okay. $8.5, wow. Obviously, you're not all doing it carefully. We'll find out what the closest one is. All right, you have a different coin or the same? 50. What did you get? 9 centimeters. Measure the radius of your coin. 1.25. All right, anyone else get anything much different than that? How about that $50 coin? What did you get? 1.35. Okay. All right. Now, here's the test. Let's calculate 2 pi r. All right, so get out your calculator, calculate 2 pi times r. And what about the $50 coin? 8.48. So if you had actually done this carefully, and not as sloppily as it seemed, you should get, if there's no slipping, this number should equal that number. That means there's no slipping. It's not so easy to do it without slipping. That's actually hard to do, especially on these smooth surfaces. What does that say? It says that the speed of this particle going around is the same as the speed of the object going that way. So the speed on the surface is equal to the speed of the center mass if there's no slipping. So we have this result, no slipping. Okay, so we'll use that fact. All right, so now what we're going to do is we're going to calculate the kinetic energy due to an object that is rolling without slipping. So we're going to calculate the kinetic energy of an object that's rolling without slipping. All right, and I'm going to do it just like before. And I'm going to put in a whole bunch of results. So the first step I'm going to write is this. The relative velocity, of the ith particle in the x direction, x is this way, is the velocity of the center mass plus the relative velocity in the x direction. And the velocity in the y direction is just the relative velocity in the y direction. Okay. Okay. All right. And the reason for this is the velocity of center mass is the velocity of center mass in the x direction, right? And there's no slipping. All right? All righty. Now I'm going to start writing some things down. Watch this. Okay. I want you to draw a picture to show this. So on your picture, you have to show where theta is. And you have to show it how it's rotating and why the velocity can be written that way. All right, and I'll give you a little hint. Ri equals the position, radius, relative to the center of mass. Okay? So Ri is relative to the center of mass. Okay? So when we think about it, remember, if this is rolling, we're going to be taking as our axis of rotation an axis that goes through the center of mass. So if it's rolling like this, our axis is right there, or right there, right there. Draw a picture. See if you can figure out what that picture should look like. I'll give you a hint. Your picture should have a circle in it. And maybe axes. All right? Pick a point on that circle and figure out how its velocity is related to the oscillation. So remember, it's rotating like this. So I'm going to draw a point on here. This is my ith point. There we have a radius vector. Ri. This is theta. Which way is the vector here? This way or this way? Up or down? Is it up or down? Up. All right, so you think it's going like this. So this thing is rotating like this, and this vector is going that way. Is that correct? It's down, right? Because we're rotating like this. We're going that way. So this point particle is going down. For acute angle, for angles less than 90, is the x component of this vector positive or negative? This has an x component and it has a y component. Is the x component positive or negative on that picture? Positive. Is it positive in my equation? Yes. All right. What about the y component? Is it positive or negative? All right. Is it negative in this equation? Yes. Good. All right. Okay. Now, how do I know it's the sine here and the cosine here? Any ideas? Usually we write cosine for x. But in this case, it's the sine. Why? Well, one easy way to see it is, let's let theta equal 0. What's the x component of the velocity if theta is 0? 0. What is it over here? 0. That's why it has to be the sine of theta. You can do the same thing for the cosine. All right. So now we have this. All right. Calculate the kinetic energy of the ith particle. So I want you to put in what we have from here, put it in there and work it out. See if anything cancels, if you can simplify it in any way. Whatever you can do. So put it in, and you have it. So Vix has this plus that. You have to square that, and then you have to square that. 1/2 mi. That's the one that's good. And then what? Sine theta? And that's plus. And then there's actually only one more term. Because sine squared plus cosine squared equals what? What does sine squared plus cosine squared equal? 1. So what's the last term? Times omega squared. Now the next step is to sum this over all ki. All of these. So the total k is the sum ki. So all I'm going to do is write in a summation sign here. So now here's a trick. Does anyone see something, one of those terms is 0? Does anyone see which one and why? One of these terms. Let's go term by term. Is this term 0? The sum mi times this? Is VCM 0? No. Is the sum over the masses 0? No. What is it? It's the mass of the object, right? So the first term is 1/2 the mass of the object times the center mass squared. What about the second term? Anyone recognize the second term? Not the second, the third term, this one. This. Anyone recognize that? I, there's an I in there. That's a 1/2 I omega squared. But it's a very special I. What's special about it? What axis did we choose? We chose an axis through the center of mass. So we should label this Cm. It's only valid, the result here is valid because we chose an axis through the center of mass, which for a disk or a sphere is right through the middle. What about this last term? Any ideas? So what this last term is, it's the velocity. It comes from this, right? It's the velocity relative to the center of mass, the velocity relative to the center of mass summed over all the objects, all the pieces in the object. What is the velocity of center of mass relative to the center of mass? What is the velocity of the object relative to the center of mass? When it's rotating, it's 0 because it's relative to the center of mass. So this term, summed up, only when you sum it, is equal to 0. One way of thinking about it is some of the particles are moving one way and some are moving the other way, right? These guys up here are rotating like this. These guys down here are rotating that way. So they're going to cancel out. So this is the final answer. So it's pretty amazing. We can view the rolling of an object as having two parts to its kinetic energy. The kinetic energy of the center of mass, as if it wasn't rolling at all, plus the kinetic energy about the center of mass. And we have one other nice result. Remember, V equals R omega. On the surface of this object, we know that that V is the same as V center mass. So we can write this when there's no slipping. And this is the radius of the object. And this is the radius. All right? So in a lot of problems, it can be written in terms of this or vice versa. The velocity of center of mass is the radius of the object times its angular velocity. We have two inclined planes. They both have the same angle, same height. On one inclined plane, I put a cylinder, and it rolls down with no slipping. In the other, I put a box that slides down, and there's no friction. Which one will get to the bottom first? The box. Why do you say that? Why would the box get there first? First of all, what do you want to use? What law of physics do you want to use? Conservation of energy. So here's the kinetic energy at the bottom. They both have the same potential energy at the top. That's at the bottom. So since this is at the bottom, which one will have a higher velocity at the bottom? We know that for the box, we just set this equal to mgh. But now for the rolling guy, we got to set this whole thing equal to mgh. So since we're adding to this, that means the velocity is going to be smaller. And we can always write this omega in terms of V center mass over R. All that's going to do is just add more. It's just going to make it clearer. So the kinetic energy, the total kinetic energy is made up of two parts. There's more effective mass. There's the mass of the object, plus there's the mass, the rotating part due to that. So does everybody see that? the rolling cylinder, let's consider the following. I have a cylinder where all the mass is on the edge. It's like a can rolling down. It's not a solid cylinder. All the mass is at the end. And then I have another cylinder. It has the same mass as the first one, but the mass is distributed throughout the whole cylinder, and it has the same radius. So both have the same radius. Okay? Which one will reach the ground first? The solid cylinder, where the mass is distributed, or the cylinder where the mass is all on the edge, and they have the same radius. What quantity is it that I need to focus on? Moment of inertia, good. Which one has a higher moment of inertia? The one where the mass is all on the surface or where it's distributed? Surface. Why? R is bigger on the surface. When the mass is distributed inside, some of those masses have smaller r's, right? So some of them, if this is the circle, some of them that I'm adding up are down here. But if all the mass is on the surface, then they all have the same large r. Okay, so the moment of inertia for the cylinder where the mass is at the surface is the largest. So will that cylinder reach the ground first or last? Use the same logic we did before. He said the one with the mass on the surface is the one that will be last to reach the ground. And that is, I think, correct. Because it has a larger moment of inertia, that means that this term will be bigger. So more of the kinetic energy has to go into that. And so we have to make the velocity smaller in order for the sum to equal mgh. All right, you could play this kind of game with all kinds of objects and all kinds of moments of inertia. Let's see, I need a volunteer. I'm not going to have to do much, no calculations. You just have to try to turn me around. Take my shoulder and just push me around. That's it. That's it. All right. All right, good. All right, good. So he did that. All right, now do it with push on my hand and do the same thing. Which one was easier?
The latter one.
The latter one. All right, now stand over there a bit and push towards me. Am I rotating? What you notice here is that when it comes to rotation, it's not just how much force you apply, but where you apply it and what direction you apply it that matters. Okay? So the simplest situation is where you apply the force tangential, right? Not towards the center of rotation, but tangential to it. All right? So let's write down Newton's second law. And we know a particle on the surface, if I'm rotating, right there, it has some tangential force, is the mass of a little particle up here times its tangential acceleration. Okay? And so this means tangential. Now it seems like I get more bang for my buck if the distance is further. So I'm going to multiply both sides by r. And this thing we're going to call tau. It's called the torque. And then I want to use angular quantities. So A is r alpha. And then I have another r, so I have r squared alpha. And notice this is the moment of inertia for a single particle. It's the moment of inertia for a single particle. And if I sum up over all the particles, let's say all the particles of my body, then I could say that this is also true in general. So this is true not just for one particle, but for a whole object. And really only a whole rigid object. The rigid comes about because, anyone see why I have to say a rigid object? Not only I, but alpha is the same for all the particles, right? And I doesn't change, right? Both for those reasons. If I don't have a rigid object, then the I will change as I move things. And also, if I don't have a rigid object, alpha will not be the same for all the particles that are rotating. All right, so this is Newton's second law for rotation. So this is the second law for rotation. That's all how it worked. All right, so I want to list a few important results that you have to keep in mind when you're dealing with rotation. What you've learned so far is, in terms of going from rotation, from translation to rotation, all you got to do is replace the mass by the moment of inertia, the translational variables, r, v, and a, by theta, omega, and alpha. And the force gets replaced by the what? What? Torque. Let me write down a few things to keep in mind when you're doing rotation. These are the kinds of things that people make mistakes on. Number one, I already talked about. I depends on the axis of rotation, right? And we may have time to show you theorems about that. Number two, the torque also depends on the axis of rotation. Okay? That also depends on the axis. When I was turned around like this, so the torque depends on my rotating that way. Okay? But if he pushed me over like this, and I was rotating about this, there would be a different R that had to go in there. So when you compute torques, you have to specify the axis of rotation. That's very important. Only the tangential part of F provides a torque. And we'll make this more mathematical on Monday, next class. Remember when he pushed on me straight towards me? There was no tangential part of his force, and so I didn't rotate. The same is true for anything. All right, see this door? So this is very clearly indicates the importance of two things. One is where you exert the force, and also the other. So same idea as when I was there. I can push here. It's pretty easy. But if I try to push here, I have to push a lot harder to turn that door, open that door. I saw an application of this once when I was going into a big bank. I forget where this bank was. And whoever the architects were, they either were very idiotic, namely they knew no physics, or they were very evil, okay? Because they put the handle to the door very close to the axis of rotation. So it was hard to open the door to the bank. So they either did that because they didn't know what they were doing, or because they wanted to make a statement that this is a big edifice, an important building, and you need to work to get into it. I'll leave it up to you to decide what the reason was. That memory sticks in my mind for many years. Okay. And as we just showed, torque is proportional to distance to axis of rotation. Distance is sometimes given a name called the moment arm. Don't ask me why, but it's called the moment arm. And then the last one, which is very useful, is gravity provides a torque as if it was acting at the center of mass. Gravity is acting on every mass in this object, but we don't have to worry about that. We could pretend that gravity is just acting at the center of mass, which would be the center there. So I can hold this. It's probably not it's close to the center. I don't know how good a meter stick this is, but the fact that I'm holding it there, gravity is going down, it's right through the same place as my finger, means that gravity is acting as if it's right there. Okay? So whenever you deal with the force of gravity and you need to deal with its torque, just pretend that the force of gravity is acting at the center of mass of the object. And of course, the force is down. So the torque about this point here is 0. Now, can you hold one end? If he doesn't hold it tight enough, it'll turn. So it'll turn. Where is gravity acting? Right around here. What's its torque? This distance, because this is the axis of rotation over there, this distance, and then times the force of gravity, mg. Hold it over near there. Is it easier to hold it straight there, there? What do you think? He realizes the closer he holds it to center of mass, the easier it is. Why is that? What has changed? The torque has changed. The torque about his hand gets smaller as his hand moves closer to the center of mass. Torque due to gravity. The force due to gravity is mg. It never changes. But the R changes. If I move my hand closer to the center of gravity, R is from here to here. If I move it back here, it's from here to here. And I can feel it. It's harder to prevent it. Let's imagine we have a pulley here. We have a string. We have M1, MA, and MB. Let's pretend MA is greater than MB. And this is the mass of the pulley. We're going to set equal to 0. If I let this go, what's going to happen? What's going to happen? MA will fall. Yeah, because it's bigger. It's going to fall there. And you can work that out. You have T up. Let's do the free body diagram for MB. We have T. We have MBG. Then we can work out the other one for MA. We have T up. And we have MBG. So we have MBG minus T equals MBA. And then I can write for this guy. Now I'm going to choose up to be positive. So I have T minus, what am I doing? Oh, this is A. A says MB equals MB. All right, the two accelerate together. If I add these two equations, I get MA minus MB equals MA minus MB. And I get A equals, what do I get? I don't know, something. Oh, yeah. So I get ma minus mb times g equals ma plus mb times a. Okay? And then I could solve for a, and I get b. Now, let's do it with the pulley having a moment of inertia. And we have to worry about that. So let's say the moment of inertia of the pulley turns out to be 1/2 the mass of the pulley times its radius squared. But we'll just worry about that. So we still have these two equations, but this time T1 and T2, or yeah, T1 and T2 are not necessarily the same. What's the difference? Well, if it's rotating this way, then we have, what is it, T2 minus T1 is equal to IP alpha, which is IP A over. So we have that. We'd have to put that in there, and we could then solve for A. So we could subtract T1 minus T2 from here. So what do we get? So you get a different acceleration. Do you think it accelerates faster or slower? Slower. So you could work this out and see that. Is there another way you can see it using energy arguments? Remember the energy arguments we used before, right? Same idea. Now we have kinetic energy of the pulley that we have to worry about. And so that's going to slow things down. Because the shift in the potential energy has to come from the kinetic energy, right? So since the kinetic energy, some of that shift goes into the pulley, it's going to go slower. So this is the kind of thinking you want to practice when you're doing problems. And you can make up your own problems. These are not that hard, right, to make up. I think I'm going to do one more thing. There are two theorems that help you compute moments of inertia. One is called the parallel axis theorem. That theorem is proven in the text. The other is called the perpendicular axis theorem. That one's not even mentioned in the text. So I thought I would do it. All right? So we're going to look at what's called the perpendicular axis theorem. It's kind of an interesting one. And it's so easy to derive, that's why I'm going to do it. So it's called the perpendicular axis. And this is for flat objects. It's only relevant for flat objects. All right? That means thin, like a piece of paper, or a disk, or I don't know, like a CD disk. It works perfect for that. All right? So let's say here's our disk, and I have an axis coming through here. All right? So we'll call this y, x. All right? So we have three possible axes of rotation. If I want iz, then I sum up this distance ri. Right? I just sum it up over the whole thing. So it's mi ri squared, which equals mi xi squared plus yi squared. And I write that as mi. Now, why can I do that last thing? I added zi squared to both quantities. Why can I do that? The key idea here is it's a flat object. So what is zi for every mass? 0. OK. So what is this? This is the moment of inertia about which axis? The y-axis or the x-axis? Here's the y-axis. The moment of inertia about this is xi squared plus zi squared. And there's no zi. So it's just xi squared. So this is I y, and this is I x. And that's the perpendicular axis theorem. In a lot of cases, Ix and Iy are the same. Like if it's a disk, they would be the same. Or if it is a square, it would be the same. And so you can use that perpendicular axis theorem to get it. I'll just write down the answer for the parallel axis theorem. Parallel. That says that the moment of inertia about any axis is equal to the moment of inertia about the center mass plus b squared times m, and b equals the distance between two parallel axes. All right? So if you have an axis parallel to an axis through the center of mass, then you can use that. So for example, the moment of inertia about this point here is 1/2 mr squared. R is the radius. If you want the moment of inertia about here, it's, and this is through the center of mass, so it's 1/2 mr squared plus mr squared. So it would be, I guess, 3/2 mr squared. So that tells you easily what the moment of inertia is about this point. Okay, so if it's rotating around like this, so it's starting here and it's rotating around like that. Okay, so that's a useful thing to do. Imagine trying to calculate the moment of inertia about this point by doing an integral over all the masses in here. It's pretty complicated. Whereas the parallel axis theorem gives it to you just like that. All right, you should be able to prove this. The proof is in the text, so if you have problems.